Now, we introduce the definition of the net side area. Yeah. So the net side area. So the net side area actually, yeah, you got it. Okay. So the net side area actually is the area above the interval AB. Okay, interval AB minus the area below AB. Okay, below AB. So here actually for this function y equal to fx. So here actually is equal to a1 plus s3. So you are late. a1 plus s3 minus a2. Okay, minus a2. So here equal to the area above AB actually is a1 plus a3, okay? And the area below AB actually is a2. So it is equal to a1 plus a3 minus a2, okay? Minus a2. So now actually we introduced how to find the area. How to find the area actually is we have 3 steps. The first step is divided AB into n equal subintervals. N equal subintervals. So here actually is we can open some points. For here, A will be denoted by x0 and x1, x2, the xn minus 1, xn. Okay, xn actually will be denoted by p. Okay, p. And so here because here is equal subintervals. Okay, equal subintervals. So here for this x0, x1, x2, and xn, actually we have we can find the formula of xa. Okay, xn. So here we can get the first subinterval is x0 to x1. x0 to x1. So the second subinterval is x1 to x2. So the third is x2 to x3. Okay. So go on. Here the last one is xn minus 1 to xn. Okay. So this is the n subintervals. Okay. N subintervals, and the y's of each subintervals actually is what? Is delta x equal to what? Delta x equal to the total length. Okay, total length actually is b minus a. Okay, so this is the total length. Okay,
yes.
So the total length here divided into n parts. Okay, so here delta x equal to b minus a divided n. Okay, so divided n. So this is delta x. Okay, this is delta x. So this is the first step. Okay, so the second step is we need to construct. We need to over each subintervals. We construct a rectangle. Okay. So here, for the first one here, for the first subinterval, this subinterval here x0, x1. Okay. So now for example, here is x0, here is x1. here is x1, here is x0. So in this subinterval, okay, first we choose a point. We choose a point in x0, x1. Okay, this point can be the left endpoint, or the right endpoint, or the middle point, or any other point. Okay, just in this subinterval here, x1 star. Okay, x1 star, and now we use this x0 to x1 distance as the y's, and the fx1 star as the height. Okay, as the height. So here we use we construct a rectangle. So here the area of the first rectangle actually is fx1 star times delta x. Okay, times delta x. So this is the y. This is the y of the first rectangle. This is the height of the first rectangle. So this is the area of the first rectangle. So go on. Okay. Now we construct a rectangle on the second subintervals. Okay. Subintervals. So here, similarly. Okay, we choose a point here, x2 star in the second subinterval. Okay. Yes. In the second interval. So here we use x2 star as the height, and the delta x as the y, okay, as the base. So here, so what's the time? Okay, so what's the time? So how can you pass the examination? So do you know how many marks you got in the first examination? Yeah? So how can you pass the examination? No matter with me, okay? It's just your sense, okay? So I introduce the content, and how many can you understand? It's your thing, okay? It's not business with me, okay? So can you pass the examination or not pass the examination? It's not business with me, okay? It's just your thing, okay? So here, this is the area of the second rectangle. So we do it. So the last one is the fxn star times delta x. Okay. So the area of the first rectangle, the area of the second rectangle, so the area of the last one rectangle. So we do it. We sum it. So here we can find the an equal to an actually is the total area of the n rectangles. Okay. So here we can write it in use the summation sum. Okay. So f k star times delta x. Here k from 1 to n. Okay, from 1 to n. So this is the second step. Now the third step actually is take the limit. Okay, take the limit. So here the area of A. Okay, the right side area we denote it by capital A. Okay, capital A. So this capital A actually equal to what? This capital A actually equal to limit n approaches plus infinity an. Okay. The limit of an. So an is this formula. So here equal to limit n approaches plus infinity the sigma fxn star times delta x. Okay. So n. Oh no, here is k. Okay. K from 1 to n. Okay. okay, from 1 to n. So here this is the third, the three step, okay. So the first step, actually we have a name, okay. The name is by the partition, okay. Partition. So the second step actually is the summation. So the third step is take the limit. Take the limit. So here this tells us just the third step to find the left side area. Okay, left side area. But here now we can see here this is divided AB into n equal subintervals. Okay, here is equal. Okay, here is equal. And here now, here is n approaches plus infinity. Okay, n approaches plus infinity. Now we introduce a definition. The definition means that the Riemann sums. Okay, Riemann sums. The Riemann sums. So the Riemann sums actually is the same. Okay, it's find the area. So here the first is the same. Now we have three steps. Okay, the first step is also the partition. Okay, partition. So here the first step is divided the AB into n. Now here is n, not equal subintervals. Okay, not equal subintervals, and divided AB into n subintervals. Okay, n subintervals. Here is n subintervals. So the first step is divided AB into n subintervals. Okay. Now here is n subintervals. Okay. Not equal. Okay.
Step 4. Step 4.
So here is n subintervals. Okay. Not equal. Okay. So what's your question?
Step 4.
Step 4.
You tell us, step 1 was equals subs.
No. So actually now we introduce a new definition. Okay, means that the Riemann sums. Okay. So for Riemann sums here is not equal. Okay. Not equal. Here for Riemann sums here is n subintervals. Okay. These subintervals can be equal or can be not equal. Okay. Can be equal or can be not equal. So here now. So the first here is we divided AB into n subintervals. So here now, and we can get the laws. Okay. So laws actually is the first is x0. So the second here. The second here is x1. Okay. Here is x1. So x0 is less than x1, and x1 is less than x2. So here is go on. Here is less than xn minus 1, less than xn. Okay. So here is we have these nodes. Okay, these nodes. So here we have n subintervals. The first subintervals is x0 to x1. So here the first subinterval is x0 to x1. So the second subinterval is x1 to x2. Okay. So the third is x2 to x3. The last one is xn minus 1 to xn. Okay. So here the y's of the first subinterval is what? So here now delta x1 is equal to the length of this subinterval. So the length of this subinterval actually is the x1 minus x0, yeah? So here delta x1 equal to x1 minus x0. So here delta x1 denote the y's of the first subinterval. And here the y's of the second subinterval is what? Is delta x2. Delta x2 equal to what? Equal to x2 minus x1. Okay. So here this is the base of the second subinterval. The second subinterval. And for the third subinterval, so the y's of the third subinterval is delta x3 equal to x3 minus x2. Okay, minus x2. So go on. So the last one. Delta xn equal to xn minus xn minus 1, okay? So here now, delta x1, delta x2 not equal to delta x2, okay? Not equal to the delta x3, not equal to delta xn, okay? So here, this is the first step. So partition, okay, partition. So here we do not have delta x here. So the second step is the summation. Now it's the same, okay? Over each subintervals, construct a rectangle. So here, for the first one, okay, for the first subintervals, here we choose a point. We choose a point in this subintervals. For example, we take the x1 star, okay, x1 star. So here we use delta x1 as the base, okay, and fx1 star as the height. So here we can obtain the area of the first rectangle. So the first rectangle actually is fx1 star times delta x1, okay, times delta x1. So here, this is the base of the first rectangle. This is the height of the first rectangle. So this is the area. This is the area of the first rectangle. Okay. This is the area of the first rectangle. So here, now go on here. For the second subinterval, we choose a point on this subinterval. We denote by x2 star. And now we use delta x2 as the base and the fx2 star as the height. So we construct a rectangle. So here the second rectangle is fx2 star times delta x2. Okay. So here this is the rectangle. This is the area of the second rectangle. So for the third subinterval here, we choose a point x3 star, okay, x3 star, and we use delta x3 as the base of the rectangle, and fx star or fx3 star as the height, okay, as the height. So here the area of the third rectangle actually is fx3 star times delta x3, okay, times delta x3. So we do it go on, okay. For the last subinterval, okay, we choose a point xn star. So now it's the same, okay. We use delta xn as the base and the fxn star as the height. So we have the last one. The area of the last one rectangle is actually the fxn star times delta xn, okay, times delta xn. So here the sum. So here the area of the first rectangle, the second, the third, and the last one. Okay, we sum it. So here. So here this is the total area of the n rectangles. We denote by an. Okay, we denote by an. So the difference, okay, the difference with the last one we introduced the last class is the last one here is equal subinterval. Okay, but in Riemann sums, okay? But in Riemann sums here is not required to equal subintervals, okay? So here, so this is the second step, okay? Summation. So the third step is to take the limit. Take the limit here. Take the limit. So here is a equal to, now here the limit is not n approaches plus infinity, okay? Here because we know that when we denote here is equal subintervals, n approaches plus infinity actually is delta x. Delta x equal to b minus a divided n, yeah? Divided n. So n approaches plus infinity actually is delta x approaches 0, yeah? Approaches 0. So but now here the base of the n subinterval is not the same, okay? Not the same. So here we need to that delta x1 approaches 0, delta x2 approaches 0, delta xn approaches to 0, okay?
Yeah.
So here actually is we just need to the maximum, okay? The maximum of this n number, okay? The maximum. So here we denote the maximum, okay? We need to maximum, okay? Max delta xk, okay? Delta xk here. We need to maximum, okay? Maximum actually is what? This number actually is the maximum delta x1, delta x2, delta xn, okay? So here the maximum, do you know the meaning?
No.
So actually here, for example, here maximum 1 and 3. So here equal to what?
3.
So here actually take the largest number here, okay? So here max means that take the largest number between 1 and 3. So actually here is equal to 3, okay?
Yeah.
Equal to 3. For example, maximum 2, 4, and 7. So here this means that take the largest number between 2, 4, and 7. So here equal to 7, okay? So here this means that the maximum, okay, maximum delta xk here actually is means the maximum delta x1, delta x2, delta xn, okay? So here actually means that take the largest number between delta x1, delta x2, delta xn, okay? So here actually we take the limit. This limit actually is not n approaches plus infinity. Here the limit actually is delta xn, delta xk, okay? Maximum delta xk approaches 0. So here this limit actually is limit delta xk maximum delta xk approaches 0. Here sigma fxk star times delta xk, okay? Times delta xk. K runs from 1 to n, okay? K runs from 1 to n. So this is the take the limit. So here now this is so here this summation, okay? This summation actually is this summation, okay? So this summation here, this summation we give it a name. The name actually is the Riemann sums, okay? The Riemann sums. So here the Riemann sums, okay? Riemann sums. So here just take the limit of the Riemann sums, okay? The Riemann sums. So here now if the limit exists and the limit does not matter with the choice of xk star and the choice of the participation, so then we say that the function f is integral, okay? Integral number on AB. So here we have this definition. So now see page. Now we see page 294, okay? 294. This is the definition of 6.5.1. Okay? 6.1 or 5.1 definition. A function f is said to be integrable on a finite closed interval ab if the limit maximum delta xk approaches 0, the sigma fxk star times delta xk yk runs from 1 to n. Okay, this limit exists. So the first condition is the limit exists, and the limit does not depend on the choice of the participation or on the choice of the points xk star in the subintervals. So when this is the case, we denote the limit by the symbol, the integral a to b. Okay, fx equal to delta x equal to this limit. Okay. So here, which is called the definite integral of f from a to b. So the number a and b are called the lower limit. The lower limit of the integration and the upper limit of the integration. Okay. So fx is called the integrand. Okay. So here, this sign is the integrand sign. Here, a actually we call it as the lower limit. The lower limit of the integration, and b we call it as the upper limit. Okay, upper limit of the integration. So fx is the integrand. Okay, integrand. So here the definite integral actually is this is the definition of the definite integral. Okay, so the definite integral actually is a limit. Okay, it's a limit. It's a limit of a sum. Okay. So here the definite integral. Okay, the definite integral actually is a limit of Riemann sums. This part actually is the Riemann sums. Okay, this part is the Riemann sums. So here actually this is actually this is each term actually is area of a rectangle. Yeah. So here actually this is the sums of n rectangles. So here this is the Riemann sums. So we find the limit of the Riemann sums. Actually, if this limit exists and does not depend on the choice. So here does not depend on the choice of the participation or on the choice of the points xk star. Okay. So if this limit exists and does not depend on the choice of participation or on the choice of points xk star, then we say that this limit is the definite integral of fx. Okay, of fx. So here, so this is the definition. Now, let's see this notation. Okay, this notation used for the definite integral dissolves some comment. Okay, so the explanation fx dx. Okay, fx dx actually is to be the infinitesimal. Okay, decimal area of a rectangle with height fx and the infinitesimal wise dx. So here a b fx. Okay, fx dx. So here this is the area of a rectangle. So this is the height. This is the y's. Okay. So here this is the y's. So by summing, okay, by summing this infinitesimal areas, the entire area under the curve was open. Okay, was open. So the integral sample is an knowledge edge that used to indicate this summation. For us, the integral sample, and the sample dx can serve as the remainders of the definite integrals. It's actually a limit of summation, at delta xk approach is 0. So the sum that appears in definition, in this definition is called the Riemann sum. Okay, the Riemann sum. So here now we have this definition. So here now we have a question. So which kind of function is integrable, and which kind of function is not integrable? Okay. So here, integrable means what? The integrable means that actually the limit. Okay. So this limit exists. This limit exists, and this limit is does not depend on the choice of the participation or on the choice of the points xk star. Okay. So now we have a question: which kind of function? Okay. Which kind of function is integrable? Okay. And which kind of function is not integrable? Okay. So now we have this question. Okay. Now we have this question. So here, now we have this question is which kind of function is integrable, and which kind of function is not integrable? Okay, not integrable. So here, integrable means that the function or the limit of the Riemann sums exists. Okay, and the limit does not depend on the choice of the participation and on the choice of the xk star. Okay, so here this is the meaning of the integrable. So here now we first answer the first question: which kind of function is integrable? So here now let's see this. Now let's see this result. Okay, if a function f is continuous on an integram AB, then f is integrable on AB. Okay, and the right side area A between the graph f and the integram AB is A equal to the integrable or the definite integram from A to B fx dx. Okay, so here now for the first question here means that if a function is continuous, if fx is continuous on AB, okay, is on AB. If this function is continuous on this closed subintervals, then we have what? Then we have fx is integrable on AB, okay, on AB, and the definite integrable from A to B fx dx equal to what? Equal to A actually is what? A actually is the left side area, okay? Left side area actually is A1 plus for this finger, okay? A1 plus A3 minus A2, okay? So here actually it means that. So if a function is continuous on a closed interval, then this function is integrable, okay? And the definite integral of fx actually is the left side area, okay? Is the left side area. So here for this function, for this result, we do not to plot it, okay? We do not plot it. We just use it. Okay? We just use it. So here, for example, for example, for this function, for here, fx equal to sin x for this function, okay? This function on this interval from 0 to 2 pi, okay? For this function, now first we know that the sin x is a continuous function. This function is continuous on this interval, yeah? This function, okay?
Yes.
This function is continuous on this
Yes.
interval. So actually, the sin x actually is integrable on this interval, okay? So here means what? Here means 0 to 2 pi, okay? Here means 0 to 2 pi sin x dx. So this integral, okay? This definite integral exists. And this integral equal to what? Actually, we can plot the graph. We can plot the sin x, okay? The sin x, the graph of sin x actually is like this. 0 is, here is 0, here is 2 pi, okay? Here is pi. So here we denote the area above the 0 to 2 pi. Here we denote it by A1. And here, the area below 0 to 2 pi, we denote it by A2, okay? We denote it by A2. So here we denote it by, so actually this area, this definite integral actually equal to what? Equal to A1 minus A2, okay? Equal to A1 minus A2. So this is the first, okay? So now for the second example, for this example here, fx equal to cosine x. For this function, okay? For this function, also on the closed interval 0 to 2 pi, okay? For this, now we know that this function, okay? This function is continuous on this closed interval, yeah?
Yes.
So fx, so this function actually is also integrable on this closed interval, and we can plot the graph. We can plot the graph here. The graph actually is like this. Here is 2 pi, here is 0, here is 0. So here now we denote the area of this part, okay? The area of this part we denote by A1, and this part we denote by A2, this part we denote by A3, okay? So here we have the definite integral 0 to 2 pi cosine x dx, okay? So this definite integral actually is the left side area of this function, okay? So here actually equal to what? Here actually equal to A1 plus A3 minus A2, okay? Minus A2. So hyperbolic.
Tomava